Hey guys, welcome to waste generation and waste disposal. Some of this we've already covered in the fall when we did our field trip to the Sanitary landfill, but we're going to go into more detail and talk about it in terms of a slightly different lens in terms of pollution here in the spring semester. Only humans generate waste that other organisms cannot use. That makes sense if you think about it. If you think about any other creature in the natural world, their waste is used and recycled by other creatures. Humans are not that way. So we create waste that cannot easily be disposed of or is not usable to other species. Waste can be viewed as a system with inputs and outputs, and there's a pretty good diagram of this in your textbook. Outputs are defined as the waste. They're the material outputs that are not useful either to ourselves or to other creatures, and they cannot be consumed. Energy waste, which could be classified as heat, is also classified as a system output. As human societies become more affluent, they generate more waste. We talked in the fall about something called the IPAT equation. I'm going to write that right here, the IPAT equation. That A there stands for affluence. So as that affluence goes up, the impact that societies have on the environment actually increases as well because they generate more waste. The U.S. started to become a throwaway society after World War II. Prior to that point, we were reusing a lot of things. We were fixing them when we needed to and not throwing things away. It was difficult to get consumer goods. They were expensive. And so we used things until they wore out. But after World War II, the population began to increase with the baby boom. There was increasing industrialization. The U.S. was a very wealthy nation at that time. And there was cultural consumption changes that were driven by the rise of advertising culture that contributed to this idea of throwing away things when they were no longer useful. The 1950s saw a rise in advertising-driven consumer markets and planned obsolescence, which is something that I really, really hate, and a lot of people do. It's the deliberate design of a product so that it breaks and must be replaced every few years. That's just as bad as it sounds. In the 1950s, consumer goods actually began to be designed and engineered so that people would periodically have to replace them, which would keep their markets up. In the 1960s, disposable diapers came into use, which greatly increased waste, and packaging materials began to be made more of composites, which contain different mixtures of materials. A good example of this would be a juice box. That's paper and metal that's melded together. This makes those containers harder to repurpose and definitely harder to recycle. And those came into more into general use in the 1960s. So municipal solid waste, MSW, we've talked about this before. It's defined as refuse collected from households, small businesses, and institutions such as schools, prisons, municipal buildings, and hospitals. 60% of municipal solid waste comes from residences and 40% comes from commercial or institutional facilities. So the majority of it is coming from houses. Other types of waste include agricultural waste, mining waste, and industrial waste. But those types of waste do not qualify as MSW, and they're usually dealt with on site rather than being collected and taken to a disposal facility. The amount of municipal solid waste generated, both overall and per capita, has been on the rise since the 1960s. There has been a leveling out and possibly a slight downward trend in waste generation in the last few years, and I'll show you that on a graph as well. The amount of waste generated varies by season, by socioeconomic status of the person who's generating the waste. In general, the wealthy do produce more waste than the more socioeconomically disadvantaged, and by geographic location within the U.S. So here's that graph I was talking about. It's also in your book. Total municipal solid waste generation is the line in blue right here that you see, this one right here. And you can see there's an upward trend. But then there becomes a leveling off here since about 2000. The same trend is shown as per capita generation. There was an uptick and then a leveling off. And that leveling off actually began a little bit earlier, in about 1990, for per capita generation. So, and if you look here with the per capita generation, there's been a slight downward trend, and the total MSW has fluctuated kind of up and down within the same range during that same time period there. But yeah, definitely leveling off. We're not generating as much waste per person, which is good news. And this is all for the U.S., by the way. I thought this was an interesting graph. This is countries that generate the most municipal waste. And this is just OECD countries. So this is the Organization for Economic Cooperation and Development. And there's a little over 100 member countries. And they're mostly developed nations. So you can see Denmark is actually, and this is kilograms per capita. If you look here, there it is right there. So Denmark actually creates the most waste per capita, which was kind of surprising to me when I looked at that. I knew United States was high on that list, and we are number 2, but we are behind Denmark. So of developed nations, the Japanese actually produce a lower amount of waste per capita, and one of the lowest of the developed nations. Now, this doesn't include a lot of the developing nations. Developing nations tend to produce a lot less waste per capita just because they don't have the same amount of consumer goods. And there are traditional societies and tribes still existing in the world that produce almost no municipal solid waste, that everything that they produce is also consumed by their society. This is the United States municipal solid waste by source, and this was a graph from 2008. It varies just slightly from what's in your textbook, but it's in the same ballpark figures. As your textbook notes, paper is our largest category of municipal solid waste. The second is food scraps at 12.7. Now, if you look in your book, and we'll talk about this a little bit, certain things in this waste stream can actually be taken out and dealt with before it gets to a landfill. Food scraps would be one of those. Obviously, food scraps can be composted, as can yard trimmings. So the potential to take away this entire slice of the pie is there if people are willing to compost. Then we've got, of course, metals, glass, and plastics here, right, which are easily recyclable. Paper is also recyclable, although the market for paperboard is much more volatile. And so we've got the potential to reduce the waste stream in multiple areas. If we actually say paper is recyclable too, we have quite a bit of that pie that can actually be dealt with before we get to a landfill situation. So the U.S. waste stream, which is the flow of solid waste that is recycled, incinerated, placed in a solid waste landfill, or disposed of in any other way, is composed of both materials that can be composted and recycled and those that cannot. And that's part of the definition. There's recycled and then stuff that cannot be recycled. So, as I mentioned before, paper, which includes newsprint, cardboard, office paper, and box board from food storage, like cereal boxes and stuff like that, is our largest waste category here in the United States. The United States generates about 230 million metric tons of municipal solid waste annually, and about 1/3 of that is recycled. E-waste, or electronic waste, is a rapidly increasing component of municipal solid waste. E-waste is problematic. It really shouldn't be in a landfill to begin with. Many types of e-waste contain toxic heavy metals like cadmium and mercury that can potentially leak out of a landfill, leading to soil and groundwater contamination. And the, quote, recycling of e-waste is often done improperly in developing countries such as China. China uses fire and strong acids in open areas without adequate ventilation, and using no protective gear, which leads to the inhalation of toxic fumes and subsequent respiratory disease. And I'm going to mention, and this is also at the end of the PowerPoint, please read the case study on e-waste recycling in Chile at the end of your chapter. Reduce, reuse, recycle, and compost. The 3 R's, which I'm sure you guys have heard your whole lives, reduce, reuse, and recycle, are practical ways to divert materials from a waste stream. Reduction, that first one, is the optimal way to achieve a reduction in solid waste generation. This is really where we want to focus our efforts. Waste is a system, so reducing the system inputs also reduce the system outputs, which is our waste. Source reduction seeks to cut waste by reducing the use of potential waste materials in the early stages of design and manufacture. Source reduction is great because it increases energy efficiency. Because it means the manufacturing of the product produces less waste to begin with, and that can minimize the disposal process. So if you're reducing the amount of materials that go into manufacturing, then you've got a more energy efficient product. It also provides economic benefits because fewer raw materials, fewer natural resources are being expended in the manufacture of the product. So when we're talking about the greatest overall impact on reduction in waste, the actual source reduction is where we really want to focus our efforts. Reuse of a product or material that would otherwise be discarded rather than disposal allows a material to cycle within the system longer before it becomes a system output. So reuse is actually also a very good way to keep consumption of raw materials down. Reuse, this should say may instead of my. This should say may. Reuse may involve cleaning or repairing the object to keep it out of the waste stream. It also may involve energy to prepare or transport the object to someone other than the original user. So in terms of thinking about this as a system again, there may actually be energy inputs in the reuse because you have to do cleaning, maybe you have to repair the object. You may also have to transport it somewhere or prepare the object for transport. So in terms of energy inputs into the system, reuse has a higher energy input than source reduction. Flea markets, swap meets, eBay, Craigslist, and FreeCycle are all examples of people practicing creative reuse techniques. And the more we can do that, I'm going to add to that thrift stores. If you're like me and you like to go thrifting to find cool things like neat clothes or whatever, then you are actually participating in the reuse of products and materials because no new natural resources are used to create what you're buying. So the R that we've tended as a society to focus on is probably the least important R. I don't want to downplay it too much, but recycling is kind of the lowest of the 3 R's in terms of sustainability. Recycling is the process by which materials destined to become municipal solid waste are collected and converted into raw materials that are then used to produce new products. Recycling can be closed loop or open loop. You probably haven't heard of this before, so let me take you through it. A closed loop recycling is the recycling of a product into the same product. For instance, aluminum cans. When you recycle an aluminum can, the aluminum is taken out of the waste stream and it is recycled back into an aluminum can. So in theory, no new inputs of raw materials are needed for closed loop recycling. Open loop recycling, however, is when one product is recycled into another product, like making recycled soda bottles into polar fleece jackets or into plastic lumber. Open loop recycling diverts waste from the waste stream and keeps it out of the landfill, but it doesn't reduce demand for raw materials to make the original product. And I have a couple of pictures up here. You've got the bottle-to-bottle closed loop, which in this particular poster it's a glass bottle. So they're talking about disposal by the recycling trucks. It's taken to a crushing plant, and that's step to, and then the crushing plant sorts the different colors, and then it's sold back to glass manufacturers who make that back into glass bottles, and the consumer uses those glass bottles and the whole cycle starts again. Glass can be recycled in this way, although there's arguably a loss of glass quality when it's recycled. Not necessarily, but sometimes. And aluminum can be recycled this way as well. Open loop recycling is down here, and it starts over on this side with the petrochemical, what they call feedstock. This is just the raw materials. So they have petrochemical feedstock making this PET bottle. PET bottles are a type of plastic bottle. The consumer uses them, and it can go into the landfill, or if it's being recycled, waste recovery and processing. So then it says fiber manufacturer right here, right? And then consumer use again. So in this case, it's got a little polar fleece jacket right there that you can see. So that is open loop because the PET that's being recycled is not being made back into a bottle. It's being made into a different product, which does not reduce the demand for petrochemicals. Many communities now offer zero sort recycling programs. And this is, Mesquite has this, so does Dallas. You throw all your recyclables into one bin, and then it's sorted by the city at a waste transfer station. The viability of community recycling programs is based on the markets for metal, paper, plastic, and glass. There's always a demand for metal, but the market for other recyclables is highly volatile, and in some cases, it's non-existent. We talked a little bit about that when we went to the landfill. It's best not to use things to begin with because, in some cases, like, I don't know, we're talking about China, does a lot of the recycling for the West, and if they're right now not taking fiberboard or plastics, and so it's going to rapidly become not feasible for our local communities to recycle those commodities. So communities cannot continue to offer recycling programs if they're not cost effective or they can't find a market or a buyer for the recyclable materials. That's what I was just talking about. China has traditionally been an importer of recyclables from the West. It recently stopped importing recyclable waste, and this is going to be likely to negatively impact community recycling programs here in the United States. So again, recycling is important, but it's actually the last choice among the 3 R's in terms of sustainability. So composting. I don't know how many of you guys compost. I try when I can. I don't always do the best job, but I have tried in the past to do this. It actually produces really nice soil. Organic waste can be composted. Composting is the creation of organic matter, also called humus, by decomposition under controlled conditions to produce an organic rich material that enhances soil structure, cation exchange capacity, CEC, which we talked about when we talked about soil properties, and soil fertility. Composting can be done by households, outdoors in a compost pile, which is this picture right here. Indoors in a composting box, which is this picture right here, or on a larger scale by communities, which is this picture right here. And this is actually a composting facility in Edmonton, Canada. The correct carbon to nitrogen ratio for composting is 30:1. 30% carbon to 1% nitrogen. So green material like fresh vegetable scraps must be layered with brown material or dried out material like leaves or dried cut grass to promote proper bacterial decomposition. If your waste cannot be recycled or reduced or composted, then it goes to the landfill. Landfills are the primary destination for municipal solid waste in the United States. The waste can either be buried or it can be incinerated once it arrives at the landfill. Modern sanitary landfills are designed to hold municipal solid waste with as little contamination of the surrounding soil, groundwater, and air as possible. So the construction of a landfill begins with siting of the fill. The designation of a landfill locations typically through a regulatory process involving studies, written reports, and public hearings. Siting is often controversial and can be politically charged. as you guys know, and we talked about this again in the fall, landfills are not considered desirable neighbors. There is a idea of NIMBY, not in my backyard, and this means that people who have more money or more political influence may avoid a landfill in their area simply because others lack the means to mount an effective opposition. This is one of the reasons why landfills were typically in rural areas away from, where people don't normally get together and can't fight it effectively. They also tend to be disproportionately in communities of color. And that's because people who have the political means and the money to fight them kept them out of their own neighborhoods. So that's definitely something to think about when we think about where is our waste actually ending up. This is a typical sanitary landfill kind of in a cross section, and I had you guys draw this in the fall, so hopefully this is just a quick review. The thing to note here is, of course, that there is a compacted clay layer down here, which is right here. It's this kind of light colored one right there. Even if the soil is typically clay-based, which they want to site landfills on places where the soil is clay-based for obvious reasons, so that stuff doesn't leach down through it, they will still put a compacted impermeable clay layer underneath where the site is going to be located. Then you have a plastic liner, which is this red layer that you can see right down there. It's very thick, and it's designed to be puncture resistant because obviously stuff you stick in a landfill might poke it. Above that, you've got your LEACHATE collection pipes and a series of different types of gravel and granular drainage. When you put the garbage on top into here, water, of course it rains, water is going to flow through there. We're going to talk more about this in the next couple of slides. So we've got some different layers of different densities of gravel, and the LEACHATE collects in these LEACHATE collection pipes and then is sent back up to the top. Right here we've got a LEACHATE treatment system and a LEACHATE treatment plant right there. We also have a groundwater monitoring well, which is required by law. We saw those in the landfill that we went to. And then there's a methane gas recovery well here. As the food scraps and the organic waste decomposes, the methane is captured. And in this particular one, the methane is used to generate electricity, and that's what's going on right there. It can also be flared off if there's no way to have it boil water to turn a turbine to create electricity. It can be flared off, but that's less environmentally desirable. And I think I already told you about most of this. Sanitary landfills are usually sited in areas with clay-predominant soils to impede possible leachate leakage. And an additional layer of compacted clay is added below the plastic liner. Leachate, which I like to call garbage juice, is water that seeps through solid waste and removes various chemical compounds with which it comes into contact. A system of collection pipes is installed at the bottom of the fill in order to collect the leachate, which is then either put back into the fill or disposed of. Leachate must be regularly tested to meet toxicity standards. If it fails those standards, then leachate must be treated as hazardous waste, and that starts a whole new series of things that the landfill must do. Landfills must control inputs to maintain safe operation. Things that should not go into a landfill include stuff that can be recycled. You should take that out and recycle it ahead of time. And additionally, metals that could be recycled, if they're put into the landfill, when water flows over that, they contribute to the leaching of heavy metal ions. Don't put batteries in the landfill. They leach toxic metals like cadmium and lead. Any types of cleaners, oil-based paints, motor oil, antifreeze, those are all prohibited. Consumer electronics, which again, when they're exposed to water, can leach toxic metals. Appliances should not be taken to the dump. Organic waste, such as yard trimmings or food scraps. This surprises most people. These really should be composted ideally because their decomposition generates significant amounts of methane, which can, of course, build up in the landfill and it's greenhouse gas. So composting them is a better way to go. A tipping fee is a cost charged for disposing of materials in a landfill or an incinerator. Landfills are expensive to create and maintain, so tipping fees help communities recoup their costs. Higher tipping fees also may create an economic incentive for consumers to reduce their municipal solid waste destined for landfills. If cities begin to pass that higher tipping fee on to consumers, consumers may decide that they want to reduce how much they throw away. Once a landfill has reached capacity, it can be closed and then capped with soil, clay, and sometimes plastic. After capping, the landfill can be reclaimed with shallow-rooted vegetation for aesthetics and to reduce soil erosion. Now, of course, the vegetation needs to be shallow-rooted so it doesn't go down too far into the landfill and possibly puncture the clay or the plastic cap. Even after capping, the threat of escaping leachate remains. So if the capped landfills aren't vented properly, anaerobic decomposition may lead to methane and carbon dioxide buildup, creating an explosion or fire hazard. So let me just expound on that just a little bit. Once the landfill is completely capped, then there's no gases or anything escaping. So at that point, once the aerobic decomposition finishes, once those aerobic bacteria have used up all the oxygen, then anaerobic decomposition begins, and you have this buildup of methane and carbon dioxide, and that can cause an explosion or fire hazard. Kind of weird, exploding municipal solid waste dumps, but it can happen. Okay, it's time for some math. This math was taken from a partial FRQ, which was a very difficult FRQ. And they've broken it down just a little bit here. This is much more doable, and we're going to actually see the full FRQ in class, but I wanted you to kind of be aware of how this stuff can be asked. So annual precipitation at a landfill in the town of Fremont is 100 millimeters per year, and 50% of this water runs off the landfill without infiltrating the surface. The landfill has a surface area of 5,000 square meters. Underneath the landfill, the town installed a leachate collection system that's 80% effective. Any leachate not collected by the system enters the surrounding soil and groundwater. So 80% gets collected, 20% infiltrates the soil and groundwater. This leachate contains cadmium and other toxic materials. Calculate the volume of water in cubic meters that infiltrates the landfill per year. And we're also going to calculate the volume of leachate in cubic meters that's treated per year. All right, so we've got 100 millimeters per year of water that's falling on the surface. Right there, rainfall. But only 50% of it infiltrates, okay? So for the first thing that we need to do is we need to convert millimeters to meters, because all of our units here say, like, they want it to be in cubic meters here. So 100 millimeters is 0.1 meters. So we've got 0.1 meters per year of rainfall, but only 50% of that goes in. So we're going to do this in a couple of different steps. So we've got our 0.1 millimeters, 0.1 meters per year. And we're going to multiply that by our 5,000 square meters, which is the area that rain falls on. But then we're going to have to multiply that actually by our 50% or our 0.5 that infiltrates, because only 50% of that 100 millimeters or 50 millimeters actually penetrates the ground. And when we do that, we end up with 250 cubic meters per year. Years are on the bottom, and then we have meters times meters squared, which gives us meters cubed per year. And then we need to actually multiply this number by how effective our leachate system is, our leachate collection system. So what we're going to do here is we're going to take our 250 meters cubed per year, And we're going to multiply that by 0.8, which is our efficiency rate. And when we do that, we get 200 cubic meters per year. That wasn't so bad, was it? All right, now we're going to do the same math. It's basically the same setup here, but it is slightly different numbers. So they say in a neighboring landfill, there's 70%, and 70% of the annual precipitation runs off without infiltrating, and the leachate collection system is 90% effective. So they also want us to calculate cubic meters of the volume of leachate that's treated. So first we have to get the volume of water that infiltrates and then what's treated. So we're assuming the same amount of precipitation. So we're going to start with this same 0.1 meters per year. So we've got our 0.1 meters per year, and we're also assuming that it's a 5,000 meter squared, and then we're going to multiply that by its how much of the water runs off. So we've got 70% runs off, which means 30% or 0.3 is infiltrating. So let's see what that looks like. That comes up to 150 cubic meters per year of infiltrate. And that makes sense if you look at that. If less is infiltrating, then you're going to have a reduction from what you see up here. So it's just like a little quick numbers check. If 50%'s up here, then 70 and 30% down here, then this number should be smaller. All right, now we're going to take that 150, right, meters cubed per year, and we're going to multiply that by our efficiency rate of the leachate, which is 0.9. And that would give us 135 cubic meters per year of treated leachate. And again, let's compare that with what's up there at the top. That should be less leachate that is treated than our previous, because the previous one has more infiltration and the previous one has a less efficiency rate. The lower one has less infiltration and a higher efficiency rate. So is this number lower than this number? Yes, it is. There's our numbers check. Okay, don't ever skip the math. Okay, incineration is the process of burning waste materials to reduce their volume and mass, and sometimes to generate heat and or electricity. So we're going to talk about how incineration can actually generate electricity. Organic and paper waste are ideal for incineration. They burn well and they burn relatively completely, and they don't produce a lot of toxic chemicals. So there's two types of stuff that's left behind. One of those things is called bottom ash, which is non-organic residue collected at the bottom of an incinerator, hence the bottom part, and fly ash, which is non-organic residue collected from a chimney flue or from an exhaust pipe. And both of those types of ash have to be disposed of. Ash with safe levels of toxic contaminants can be disposed of in the landfill itself. So they burn up the trash coming in, and if the toxic levels are low enough, they just take that ash right back to landfill. But ash with high levels of toxic materials have to be sent to a special disposal site. They have to be treated like hazardous waste. So harmful exhaust gases that escape from incinerators, like sulfur and nitrogen oxides, can be filtered out by baghouse filters or wet scrubbers before release. And a lot of these are the same technologies that they use on the chimneys or the flues of coal burning power plants. And we'll get more to that when we talk about air pollution. Heat generated by waste incineration can be used to generate electricity in waste to energy systems. So when we are talking about how electricity is generated, right, you got to have, well, you don't have to have, but one way of doing it is to heat water to boiling, and the steam turns a turbine. So if you're heating water with this waste heat from incineration, then you can create steam to turn a turbine to create electricity. The drawbacks of incineration include that the combustion of plastic creates air pollution that causes respiratory disease. And you guys saw this when we saw Plastic Ocean. When you burn stuff that's made of plastic, there's really bad chemicals that are released from that, and it can cause all kinds of respiratory disease. The ash of incineration is more concentrated than the original municipal solid waste, and therefore those contaminants are more concentrated in the ash. Incinerators are also expensive to build and operate, and the siting of incinerators raises environmental justice issues, just as landfill siting does. If you are releasing fumes that are foul in smell, or they contain gases that can be considered air pollutants, or fly ash is coming out, any of those kinds of things, nobody really wants to live next to that for obvious reasons. And so where you stick a waste incinerator can definitely be problematic from an environmental justice standpoint. Hazardous waste is liquid, solid, gaseous, or sludge waste material that is harmful to humans or to ecosystems. Hazardous waste is generated by textile production, cleaning machinery, manufacturing electronics, dry cleaners, automobile service stations, and small farms. Households also generate hazardous waste in the form of oven cleaners, batteries, lawn fertilizers, and oil-based paints. Industrial and household hazardous waste have to be kept out of sanitary landfills. That stuff there's all kinds of regulations that deal with hazardous waste, and if it mixes with a municipal waste stream, then we've got big problems. Most communities offer collection facilities where homeowners can deposit hazardous waste for safe disposal, and that is what that is right over there. This just happens to be a poster for hazardous waste collection from a community in New York. Mesquite has collection days for household hazardous waste as well, and if you don't want to wait until the day that they collect it, you can actually take it to the collection and disposal site, just like you can in the city of Dallas. Regulation and handling of hazardous waste falls under two pieces of federal legislation: the Resource Conservation and Recovery Act, RCRA, and the Comprehensive Environmental Response, Compensation, and Liability Act, CERCLA, also known as the Superfund Act. So RCRA was passed in 1976, and it implemented cradle-to-grave tracking of hazardous waste. Now, prior to RCRA, manufacturers, there wasn't a whole lot of regulation on hazardous waste, and sometimes they didn't keep track of where they'd buried that stuff or disposed of that stuff. So when the fledgling Environmental Protection Agency came in and said, oh, where's all these barrels of dioxin that you've been producing from when you're manufacturing paper? And they're like, oh, whoopsies. I guess we lost the records on that. We just don't have really good records. This kind of held chemical manufacturers and producers responsible for what they were doing with their waste. If they were responsible for keeping a cradle-to-grave track of it, then it couldn't just get quote-unquote lost somewhere along the way. In 1984, RCRA was modified to encourage waste minimization, to begin the phasing out of the disposal of hazardous waste on land, still permitted in the ocean, and increased law enforcement authority to punish violators. CERCLA was passed in 1980. It imposed a tax on the chemical and petroleum industries to fund the cleanup of abandoned and non-operational hazardous waste sites. Hence the name Superfund, because the money from the tax was used for the Superfund, which is money to clean up these abandoned and non-operational hazardous waste sites. It also authorized the federal government to respond directly to the release or threatened release of toxic substances. So if there was some environmental disaster that occurred or was about to occur, the federal government had the authority to step in to clean it up or prevent it. And under CERCLA, the EPA maintains the National Priorities List, it's called the NPL, of highly contaminated sites that are eligible for cleanup funds. New Jersey has the dubious honor of having the highest number of Superfund sites nationally, but that state also estimates that there are about 9,000 additional sites in their state that probably need to be cleaned up before they can be redeveloped. Yay, New Jersey. So one of the case studies that you need to know about solid waste and hazardous waste disposal is Love Canal, New York. A century of hazardous waste dumping by the Hooker Chemical Company caused massive soil and groundwater contamination in this area. This is by Niagara Falls, New York, so upstate. The Hooker Company sold the land to the city of Niagara Falls for the large sum of $1. On behalf of the chemical company, they did disclose that the land was contaminated, and they told the city that building on the site would dislodge the clay cap that they had put over the waste. The city chose to build there anyway. In the late 1970s, it was shown that carcinogenic wastes such as benzene, dioxin, and trichloroethene were present in the drinking water and in the dwellings, particularly in the basements of homes and schools in the area. And that was leading to a higher than normal rate of illness and miscarriage. Love Canal was listed as a Superfund site in 1983, and all of the residents were evacuated. The physical cleanup of the site was finished in 94, and it was delisted as a Superfund site at that time. The site is now listed as not posing a threat to human health. So the Superfund works. Brownfields are contaminated industrial and commercial sites that require cleanup before they can be redeveloped or expanded. These lands have not met the conditions necessary to be in the Superfund category, so they're not that polluted, but they're problematic areas with contamination nonetheless. You probably don't know this, but I will let you know this. The American Airlines Center in downtown Dallas is actually the largest EPA brownfield project in the entire United States. So all of the land, including the parking lot and the arena itself, that area sits on used to be a very, very polluted area near downtown. So there was a city dump there. There was a meat packing plant on the same area and a retired power plant. It cost over $12 million to remediate the land before it could even be built upon, so that it would be safe for people to have, for the pipes containing the water to be taken in and all that stuff. So it was a big project, but it's a great use of land that was very marginal and was highly contaminated by some pretty unsavory businesses prior to the American Airlines Center being there. So some new ways to think about solid waste. As the human population increases and we recognize our part in the reduction of solid waste, we need to think of ways to minimize municipal solid waste and new ways to deal with it. So life cycle analysis is a systems tool that looks at the materials used and released through the lifetime of a product and the procurement of raw materials through their manufacture, use, and disposal. So, it's basically cradle to grave. What kind of raw materials go into the creation of a product? What kind of energy needs to be put into the manufacture of a good, and then how is that good disposed once it's no longer a viable product? This type of analysis can help communities determine the best way to deal with the specifics of their particular waste stream and to minimize disposal, recycling costs, and energy use. It costs cities lots of money to dispose of waste and also to recycle and or incinerate. So this life cycle analysis can help cities and municipalities reduce their costs and their energy use. Integrated waste management and disposal strategies. So integrated waste management is an approach that employs waste reduction, so source waste reduction, management and disposal strategies that are aimed at reducing the environmental impact of municipal solid waste. Integrated waste management emphasizes source waste reduction, but it also may include recycling, composting, the use of landfills, incineration, or other waste appropriate measures. The big thing here is it also seeks to change consumer behavior related to use and disposal. So, some of the things about that we've talked about the zero waste supermarkets. There's one in Austin, and then I posted a video earlier on Google Classroom about a shop in New York that was selling, basically the zero waste lifestyle. So everything in there is reusable and is designed to be used over and over and over and over and not go into the waste stream. So those are the kinds of things that integrated waste management is kind of stressing. This approach is championed by William McDonough and Michael Braungart in the book Cradle to Cradle, and its sequel, The Upcycle, both of which are on my bookshelf in the classroom if you're interested in reading them. McDonough and Braungart use the term upcycle to describe the conversion of a waste material to something of higher quality and greater value than the original product. So they're thinking in very radical ways about waste, not just downcycling or I would say lateral cycling. Downcycling would be, when we were talking about open loop recycling, where we're taking plastic bottles and creating, polar fleece fibers or something like that, or Trex decking, the plastic lumber. But actually creating something even more valuable from a waste product. We will be seeing some clips of a TED Talk that these gentlemen did that was very, very inspiring. And last but not least, please don't forget to read the case study about recycling e-waste in Chile at the end of the chapter. Anything in there is fair game for questions. Okay, have a wonderful rest of whatever you're doing, and I'll see you in class.